Welcome! Today, my group and I will be presenting our final project in our module on data engineering in the cloud. In this project, we developed a full end-to-end cloud-based data pipeline in Amazon Web Services to provide up-to-date insights on India's COVID-19 situation. This batch processing pipeline was built in Lambda. It automatically extracts, transforms, and loads data into a Tableau dashboard which automatically updates itself with new data every day. This provides actionable insights based on current and past data. Does that sound cool? Want to see the various technicalities behind how it all works? Let's get right into the presentation.
Alright, cool. Okay, good morning, Mrs. Zaw and friends. Alright, so we're Group 2 and today we're presenting our DAEC data pipeline for the India COVID tracker done in AWS. So that's a brief overview of the contents. I'm going to read them all. And we'll start to look at first a little bit of refresher for the pipeline diagram. The pipeline diagram has remained roughly the same since part 1. But with one key point that we also mentioned in part 1 too, is that we're getting rid of the streaming layer because we really can't justify it with the next points. For these 3 points here. So the non-inclusion of the streaming layer is due to the low API update frequency, which even at its peak was about 1 day, which is still not ideal for streaming, but has now gone to 1 week, which again is not a good candidate for streaming. As such, it has poor cost to benefit ratio. The high cost of streaming cannot be justified because we don't really have much of a use for it. And there's unlikely resurgence of COVID in India based on local and global COVID trends. That's not very likely that COVID is going to come back again. And so streaming likely to be necessary. Now moving on to Nathan.
Yeah, so we actually translated this pipeline diagram into AWS step functions. So what is AWS step functions? It is our workflow orchestration. As you can see here, workflow orchestration is when we put all of the steps in each individual step all into one giant function that contains our entire data pipeline. So as you can see from the top one, this one is ingestion and storage. This does process and serving, and we also have error handling built into our step functions. So we'll go into more detail later on in the presentation. So for now, I'll hand it over to Joel, who will be doing the first section on data ingestion.
Thank you, Nathan. So as data, we're talking about data ingestion. This is just the part where we take the data from our source and move it into storage. Yeah. So we start with our Lambda function. The big premise of this is just getting the JSON file from our source and from its nested structure, using nested for loops to turn it into a list of dictionaries where each dictionary within the list represents one row of our data. From this list, we just write it into a CSV format and then we move it into our S3 bucket. So to activate the function, we use 2 triggers, CloudWatch Event Bridge to run it on a set schedule of 1 day, and the API gateway so we can use an API endpoint to call it whenever we want. So as for particular configurations, we increase the timeout period from 3 seconds to 59 seconds. It just gives us enough time to run the function. From our experience, it takes maybe 6 to 8 seconds to run. So giving us this bit of grace period just lets us ensure that it finishes running. As well, we increase the memory from 128 to 512 megabytes just to give ourselves a bit more resources to work with. Also here, you can see that we have the endpoint created as well as the API key. We set this as our security mechanism so that we can ensure that not just everyone can run our function. Moving on, we'll move on to like a quick demo. We have a command line expression that will send a request over to our API. So as you can see here, it returns the name of that CSV. And I think if we go into our S3 bucket and we hit refresh, it's a bit hard to tell, but you
It's all the way there.
You just see the date.
okay.
It's 9:41, it's 9:42 now.
Yeah. So you can see here, that's the file. And yeah, so that's our demo done. We'll move on to Zhao T for storage.
Okay, can. Thank you, Joel. So now I'll be explaining why we need data storage, or the files that we use for data storage. So the main reasons why we need data storage is because of the exponential growth of data over the years, to make it more secure and organized, and also it's easy and efficient for us to use. Now we're talking about why we use S3. Now the reason why we use S3 is because it's scalable, durable, is cost effective, flexible, and also is high security. Now the bucket we created was used with the default settings, but these are some of the unique configurations within the bucket that we changed. So we'll be talking about the bucket versioning, lifecycle rule, MRAP, and also the transfer acceleration. Okay, so bucket versioning basically keeps multiple versions of the object in the bucket itself, and each version has a unique ID. Now, the reason why we use this is because we need to retrieve and restore in case of any issues, and also ensures the continuity of the itself. Now, the only downside is that there's a slight increase in price, but other than that, it's working very well. Okay, now we move on to the lifecycle rule configuration, where basically it's just a rule to either transition, expand, or delete the object itself in the bucket. And why we use this is because it's more cost effective for us to move it to a long-term storage, and also is more organized. Now, the downside is there is a slight increase when it comes to the retrieval price itself. As you can see over here, I set it so that after 14 days, the objects will expire from current to non-current. And then from there, after 16 days, which 1 month since we collected data, it will be moved to Glacier Instant Retrieval, where you can access every once a quarter. And after a total of 3 months, you receive the data, it will be deleted from the bucket itself. Now, we also set up MRAP, which is multi-region access points. And the reason for this is because it can be used anywhere, and it allows us to all work on the projects, even if we are in different countries around the world. And lastly, we use transfer acceleration, mainly just to have an accelerated endpoint, and also just makes it more efficient and faster data transfer itself. Although on the downside, there is a slight increase in price, which will be heard when we use it. Now I'll pass the time on to the data process, which is done by Kevin.
Thank you, Zhao. So I'll start by first explaining the purpose of having the data process. So at this stage, we extract the structured data from a temporary storage, and we will be preparing a table schema for the data to be loaded into. So the column data type should be manually adjusted if they are incorrectly recognized. See an example of later. So for the AWS services and components used, or the temporary storage used will be S3, where we will store the unprocessed data to be processed in data brew, as well as Glue Data Brew itself, where we will take the data stored in the S3 bucket and create a table schema where the data types will be automatically assigned. Now let's take a further look at the pipeline in AWS itself. So by creating a new project and sourcing the input data set to the S3 bucket, we can import the data set into Data Brew. And the data set will appear here. So should I continue? Yeah, so it talks about the date. Yeah, so okay, upon further exploration, right? As mentioned earlier, the data types will be automatically assigned. However, there's a date column that was incorrect, not say incorrectly assigned, but it was assigned like as you can see here, there was a date column that was date time format. However, the time section was just 000 and it's unnecessary. So it takes up unnecessary space, and hence one measure we took to change that was we convert the date time format to date format for the. After that, this is the only change we make to the dataset, and after that we're ready to proceed to. After that, we're ready to proceed to the data serving layer covered by.
Alright, thank you so much, Kevin, and I'll be doing the data serving layer. So in our data serving stage, we have 3 key components or 3 key points that we have to do. The first is data wrangling, which involves transformation of source data. The second is setting up the VPC, which configures Data Brew and other consumers to access our Redshift cluster. And then third, we have loading into Redshift using our Data Brew job. So I'll go through that one by one in detail. The first step we'll be going through is data wrangling. So data wrangling was all done in the Glue Data Brew project. The first type of data wrangling that we're doing is data cleaning, and then we'll be moving on to integration and also creation of calculated fields. So for data cleaning, for the missing values that we see here, we notice that for 2 consecutive days, for example, you'll see here 26th of December to 27th of December, we actually have the same values for all. And of course, this is the cumulative total. So what does this mean? This means that there was 0 because delta is the change between days. So if they are the same, that means there was 0 change. And 0 change means that all of these null values actually should be replaced with 0. And so this is what we found throughout the data set. So we actually changed that, we fill the missing values for confirmed, deceased, recovered, tested, and other. Then secondly, we remove the anomalies in the data. So we see negative values, for example, in vaccinated, tested, deceased, surprisingly, and other. So obviously, this is not possible because you can't unvaccinate people, and so there's no negative values. We have to replace that with 0. Then the second step that we took was data integration. So we actually created the population estimate for 2023, which we sourced online. For each state, we got the population, which actually helps a lot in analysis, as you will see later on in the analysis stage. For the India state names, we also put in the full state names corresponding to each state code that was in the data set. As for the calculated fields, this is where it gets interesting. We look at the active cases, which is the number of confirmed cases minus recovered, minus deceased, minus other. And of course, we have other metrics that are very useful to healthcare professionals, such as the test positivity ratio, meaning how many you test and what proportion of them is confirmed cases, and also the case fatality ratio, albeit this is a little bit morbid. Of course, we also have the vaccinated proportion, which actually talks about how many percent of the population in each state is vaccinated with 1 dose, 2 doses, which is fully vaccinated, and how many have gotten their booster shot. The second step is to set up the VPC. Because we have all the data transformed already in DataBrew, but we need to put it in a place where other consumers can access this data. So for us, this is called the serving layer, and then we actually use Redshift as our serving layer. So we configure DataBrew and other consumers to be able to access. So for DataBrew to be able to write to the serving layer, and for other consumers to be able to get the data from the serving layer to be used in analysis and for other purposes. So these are the 3 steps for setting up the VPC. First, we need to connect the VPC endpoint. After that, we need to get the NAT gateway so that private resources can access the internet. And then we'll be talking about the custom security group, which this is a very important part, which we will be discussing right now. I'll do a demonstration for the custom security group part. So if we go into VPC management console, you'll notice that we created a few security groups here. This first one about allowing port 5439. This port 5439 is used for other sources to access Redshift. So if we go into inbound rules, you'll notice that I added my home network. However, right now we're not connected to my home network right now. So if we go to Redshift here in, for example, Tableau is actually an example of a consumer. So I'll copy the endpoint for our Redshift, put it in here, and then I'll put in the password. So you notice that while we're executing a query, it wouldn't work. And why does it not work? That's because our inbound rules for our security group doesn't include our current network that we're connected to, which is TP's network. So you notice that the Tableau just doesn't really work right now. So if I click cancel, I'm going to cancel this request, and then now I'm going to add a rule. So based on our research, we actually found out that the DNS for Temasek Poly is the IP range or subnet is 152.226.0.0/16. So I'm going to put that into the inbound rules here. I'm going to put in Redshift and put in the header notation 52.22.0.0/16. And then I'll put here TP subnet. And now I'm going to save the rules, and we're going to edit the inbound rules. It says here that it's successfully modified. So now that it's successfully modified, we should be able to go back into Tableau and get it working. So let's see if it does. And as you can see, we are successfully loaded up Tableau. And when we go into the schema, we are able to find our table as well. I'm going to try and drag the table and click update now. And yes, all of the data is successfully loaded into Tableau once we have all the correct security groups. So in order to maintain security, besides using username and password for our Redshift cluster, we'll be limiting which IP address ranges are allowed to access our Redshift cluster. As you can see just now, if we are in a network that isn't in these inbound rules, it will simply not work because it will get blocked. And with that, I'll move on into the last stage of our data serving layer, which is the data brew job. So what is a job? A job is basically a task that is automated and actually takes the input data, transform it through data brew, and then outputs it into our serving layer. How does that work? Again, we'll have another demonstration. You can see here that our recipe jobs, we have a DAEC connect to Redshift, which I will show the details now. Under actions, edit. So you can see that it takes our associated source data, applies all of the transformations that we have done in the recipe, and then we output first to Amazon S3 as a backup. As you can see here, DAEC serving layer backup. And then more importantly, we output to Amazon Redshift. So this Redshift creates a new table in our Redshift database where the data can be accessed. And with that, this ends my section, and we'll move on to Ashley for monitoring.
Thank you, Nathan. Okay, so now we move on to monitoring. So what monitoring is basically we track and analyze performances. Analyze performances. Okay. So what we look at is actually for Lambda, we look at the duration, the errors, the invocation count of each run, the memory, and the CPU usage. So what this actually does is to gain insight into health and efficiency, identify and troubleshoot problems, and optimize the performance for Lambda functions. So what we use for the AWS services and components use is CloudWatch, Simple Notification Service, also known as SNS, and Lambda. So what is CloudWatch for? It's used for metrics gathering, log archiving and analysis, and setting alarms. SNS enables us to deliver notifications or emails for other endpoints. And Lambda is used to automate the process of compiling relevant error, send out to the relevant SNS topics. Okay, sorry. Then we move on to the demonstration of how to create SNS. Okay, so first we have to create a topic. So a topic is a logical access point that can receive messages from publishers. So usually we use the standard thing, and then we name it like a certain name or anything. But in this case, we already have so we don't create for now. But you have to use a unique name identifier. So now we move on to subscribers. So what these subscribers actually is they are endpoints that can receive messages from our topics. So you can create subscriptions from SMS, emails, and etc. But for now, we actually just use Nathan's number and as well as his email for this presentation. Okay. So how to create a subscription is basically you go to subscription over there. Okay, then after that you have to enter in the relevant RAN, and then for this protocol we will just use email or SMS. But then in this case we already created, so we're not going to do that. Thank you. Okay, so not done yet. Okay, so we have two left, right? Okay, so then now we move on to the Lambda function in order for this to work. So in this Lambda function, right, we actually created we make sure that the filter pattern is triggered by any form of error. So it will be in details. So here the CloudWatch logs, and then it will be in details. Yeah. So actually by this the filter pattern is error. So what this question mark does is it acts as a wildcard. So whatever errors that goes through, it will just automatically trigger this, and then after that we'll send a SNS notification to our respective endpoints. So that So now Nathan will show you an example of an error and how it will be sent to our respective endpoint. So that it's functional. So over here we have an error. Let's say we have an error over here. Yeah. and then we deploy it. Okay. Okay, and then actually we can see the error over here. So it takes any form of error. It doesn't matter what. And then they will also send the email. I think it will take quite a while to load first. Yeah, they send the email. You can see over here. Okay, next we move on to the operational class. Operational dashboard actually. At the okay, so this is our operational dashboard lah. So from here, what we can actually tell is that our Redshift is generally working normally lah. This is what a normal dashboard will look like, with no problems detected. However, it is still important to monitor our performances so that we can take corrective actions before it happens. So who would actually benefit from this dashboard? It will mainly be operation teams, because they can use the dashboard to monitor and troubleshoot the infrastructure issues, so that they can, and we can use the glass to also identify performance anomalies and track resource utilization and monitor the system health. Thank you. Now we move on to Joshua for the data analysis.
Alright, okay, thank you very much, Ashley. Okay, so now I'll be covering the more customer-facing role, which is data analysis. Right, so let's do a little bit of introduction first. This stage is to extract meaningful insights and information from the data that has been processed through all of our efforts and transform through the pipeline. The focus on it will be providing users with actionable insights that can be used to identify patterns in infection and track the growth of a pandemic, etc. So we went through it with two routes actually. The original idea was to use QuickSight, but upon further research, we decided to go with Tableau via the Redshift connection. Okay, so we end up choosing Tableau on the rounds of functionality and customization because it's a lot more mature. Tableau is a lot more mature software as compared to QuickSight, and it's just better, frankly. Tableau is just better than QuickSight. But QuickSight, we have still found a use for it. We kept it as our backup system. Right? We can show you how the QuickSight works if you're interested. The QuickSight, you want to show? Fantastic. Okay, next. Right, so we'll take a little further look at this stage in Tableau, no longer QuickSight. Okay, cool. As Nathan demonstrated a little bit earlier on, this is the connected data set. It updates automatically, and you can update it by yourself if you like. There's a refresh button down here. We want to update the data automatically. And we go over to the dashboard. So on the whole, this is what our dashboard looks like. You can see some points that we brought up last time around, like testing rate over time, infection rate, death rate, case fatality ratio that Nathan kindly brought up earlier on. And so this dashboard is pretty much just to allow the user to play with it as much as they like, right? To go and find insights on their own. But we have decided to come up with a bit of a data story just so that we can show what a user may think when they encounter the data set or when they encounter this dashboard. So this is a trial data story. And so the first one, if we follow their story, is that good news. Only 2 significant spikes in infection rate across all of India. It's fantastic lah. And these 2 spikes slightly correlate to the introduction of variants of COVID, like remember saying Delta and etc. And next. And this could also be due to India ramping up testing, which of course if you increase testing, you naturally increase your own infection rates. And as seen from here, the spikes are actually very closely matched. So the spikes are where they're supposed to be, and they're very closely correlated to the spikes in the first graph. However, there is another spike over here, which is semi-unexplained, but it's likely due to the introduction of testing, the quick introduction of testing, that ramped up the ratio temporarily. So we're going to look at something a bit more morbid, and that's statistics, which is very fun to look at, is that the major spike takes place between Feb and June 2021 and appears to coincide with the peak of the pandemic. This is a bit tragic, 57,000 deaths in 1 week. This spike follows a dip in deaths, so a possible explanation for it could just be some rollover from the dip here, because there's an uncommonly low dip before the rise up here. So it could just be rollover. We're hoping it is. And as well, we kind of can see over here as well that there's an enormous spike that correlates to, and this spike actually follows a generally even line here. As such, again, we say the possible reason for the spike could just be rollover from the dips again. And now we look at the vaccination rollout. So the three colors here, they are all individual vaccinations. So blue is booster, orange color is 1 vaccination, red color is 2. Right? And we can see that there's a rather large gap here between the start of the pandemic and the start of the vaccination program that could have been a cause for the large number of infections and deaths early into the pandemic. And tragically, up to today, many Indian states still do not have a high proportion of fully vaccinated Indians. You can see here that orange has fewer fully vaccinated Indians in the state, and blue has more. The orange is still quite prevalent. So we start looking a little bit deeper in. We'll start looking at like a state-by-state basis. State-by-state basis. So we look at another state called Sikkim, which has a very good 100% fully vaccinated rate by all counts. They seem to have I think I have to reclick it. Yeah. Yep, okay, there we go. Sorry, the chart was a little bit wrong. Right, so we can see the state seems to have taken a approach on multiple rounds of mass vaccinations. Going to see mass vaccination 1, mass vaccination 2, mass vaccination 3, and technically mass vaccination 4. Right, with the focus of fully vaccinating their citizens up to at least a second vaccine, which may have provided a more consistent level of COVID protection for all of its citizens. Now the comparison is to the state of Mahalaya, if I pronounce it right, where the state seems to have taken a more approach on focusing more on the first vaccination. As we can see here, the intention is more on the first, or the intention is to more vaccinate or to give their citizens the first vaccination, which is again in contrast to the previous one. There's no spikes here. There's just an even throughout. And this could be due to the comparatively larger number of citizens in Mahalaya, 3.3 million to the to the about 700k. So that could be another reason as well, but this is from our own observations. And the slow rollout of the second vaccine may have contributed to the large number of infections from within the state. We confirmed that smaller states such as the Andaman and Nicobar Islands, they actually tend to handle the pandemic better. Logically, that is consistent. The Andaman and Nicobar Islands, in comparison, have an increased emphasis on the second vaccine, as you can see here. And they were able to roll out again in spikes, and they were able to fully vaccinate their citizens as well. And furthermore, this state sees, a larger spike in booster vaccinations, which also leads into increased protection for its citizens. So we're rolling into a conclusion that one of our users may have from this data, and may have from the dashboard that's created, is that the states that share the following characteristics of intervals of mass vaccination, smaller population, and heavier emphasis on fully vaccinating their citizens, tend to provide a more consistent level of COVID protection and help the states to weather the pandemic better. So that brings us to the end of this. And so in here already, I'll hand the time over to Nathan for the self-directed learning.
Alright, so we have a couple of learning points in this that we have done from this project. The first learning point is how we have actually experienced doing extract, transform, load processes and data pipeline in the cloud. So we have been familiar with ETL ever since data warehousing subject. However, this project has opened our eyes to actually doing these pipelines automated in the cloud, and of course not depending on any on-premises hardware to perform those tasks. Our second one is scheduling and workflow orchestration, which we have discussed in AWS step function. We actually have our step functions also run on the schedule. So our entire data pipeline is automated. It runs automatically without user intervention, and it runs on a regular basis. And if there's any issues with our scheduling, or when there's any issues with the data pipeline execution, it will automatically send a message to the system administrator via email and text message. Then the third thing is, of course, you learn how to gain insights from ever-changing data sources. So all of our previous projects thus far has always been based on historical data, meaning data sets that are already present, they're already there, and they contain past data. However, this project actually allows us to update with live information all the time, pretty much every day, we are actually updating our Tableau dashboard, our story. We are updating it with new data every day because of our scheduling that we have done. And the fourth part is planning and structure of our project, because this is a relatively big project with a lot of interdependencies between the individual components. So it's also very procedural, and that is the method that we took. We started off one step at a time, and then this is how we managed to complete our project.
Actually, if I can tag on to the third point as well, this leads back to data visualization. The dashboards we created, the insights can actually change over time. So, the next day, some data could come out that, they're not necessarily the islands that I mentioned a little bit earlier on. They could have the best vaccination rate, they could have the worst by the next day. So it's all dependent, all fluid. But the point being is that the dashboard is able to accommodate this. It shows changes over time, and it's a time slider if you wish to see things again over time.
Alright, so some of the setbacks that we faced when developing our proof of concept. The first was definitely dealing with our nested JSON structure, which we all know was a little bit of a challenge. It was deeply nested, very hard to deal with at first, but we realized that we could use nested for loops in Python. Of course, we also had issues with Lambda runtime, which I think on Joel's end was the time execution limit, which was only 3 seconds. So we actually, as he mentioned, we resolved that by making it a little bit longer and by setting more resources to it. Then of course we had our output to Redshift, which had some issues with the endpoint early on in the project. And this one was, I think, every group's worst nightmare, the access to Redshift part, where we required a creation of NAT gateway and adjusted custom security group for better security. And I think, as you can probably attest to with our constant conversations about the step functions, we definitely had step functions issues from the get-go. That was also because of some issues that I had in the configuration of the step functions. But again, with the support of AWS support team, and of course with your kind of support as well, we managed to figure out the problem, which is the IAM role as state input. Then of course we also have the AWS credit limit, which all of us have tried to exercise great care whenever we are using
Very
pricey,
delicate and great.
very, very delicate care when using pricey AWS services like VPC, EC2, and other services. And also for now, I also want to go on to go back to the step functions as earlier promised. Alright, so our step function execution, this is our overall flow. This is a successful execution of our entire data pipeline. And if you look at the timing, we executed it earlier today at 8:33 where it completed. I'll go through the state machine in detail as well in the workflow studio. Make this a little bit smaller and shrink this. Okay, so first we start out with the Lambda function, which has ingestion. Alright, so we start off with the first one, which is ingestion plus storage. So this one is our Lambda function, which, as mentioned by Joel earlier on, it actually takes the data from the JSON structure and then it puts it into S3. However, our Lambda function also has a special feature that it outputs different status codes depending on whether it works or not. So you can see the rule here. We actually set for the success criteria, we actually use our status code. Okay, this one here is a bit bigger. Status code equals to 200 OK, which is a way of HTTP request, which actually shows that it's successful. And in case that it's OK, we will move on to data brew, which is the next step. Of course, if it's not OK, if it's not successful, we actually have another rule that when the status code is 400, it will automatically publish to the SNS topic. How does this work? It's also because of the Lambda function. We actually have a try except clause. So by using a try except clause, we actually make sure that all of the exceptions are caught successfully, and all of the errors can actually be logged by the SNS topic as well. Then when we move on to data brew, the start job run, which is over here, this actually just runs the data brew project, which we have discussed earlier. So the data brew runs completely automatically. It does the entire process and serving stage for us. And then after that, we have the housekeeping stage. So this is another fun part. We actually have a housekeeping stage for our S3 as well. So it automatically deletes older files. And how does this work? We actually have a custom Lambda function for that. So let me just show you. This is an overview of how the code works. we actually get the date time minus 30 days, meaning that all the files that are older than 30 days will be automatically just purged out of the S3 bucket automatically. And no matter whether it's whether there's actually stuff being purged or not, you'll be able to see in CloudWatch because of the JSON.dumps result. And then when we move on from there, if it's successful, status code 200, it will return a success state on our state machine, else it will return a fail state. So this is our state machine, this is our data pipeline that we have developed. So we'll move on to Joshua for the conclusion stage.
Alright, so finally at the concluding remarks, which I think some people are quite excited for. Right, so the concluding remarks is that all stages and services have been successfully implemented. Remember the diagram that you showed earlier on? Everything you see in the diagram, every little part has all been added. So the POC pipeline meets the lead data scientist needs for feasibility and being economical. And we have to note that weaknesses of pipelines were addressed. So contingencies were available at every stage to counter potential weaknesses that we found in the in the part 1. But we also must note that there was still a main weakness. The pipeline is susceptible to cost overruns, as some have experienced before. And on our end, if streaming ends up being implemented, or does end up being implemented, then the cost of running the pipeline is likely to grow beyond scope and to exceed feasibility. But ultimately, we'd just like to say that the pipeline has met expectations and is very much ready to be implemented. And we would recommend the implementation of this prototype pipeline in future projects. With that, thank you very much for your attention.
Thank you.
You have any questions? There we go. Okay, sorry sir, do you have any questions?
Do you have any questions for us?
Increase cost.
Credit limit.
Increase credit limit, yeah.
Increase credit limit or sharing your credit limit, that will be excellent.
Increase credit limit or sharing a credit limit and IAM.
Yeah,
IAM issues, yeah. IAM unlock issues as well.
Yeah.
Okay.
Thank you very much, Mr.
Yeah,
Zong.
thank you very much.
Thank you for teaching us the subject too.
No question. No question? Would you like? Okay.
Alright.
What was the question?
Thank
Okay.
you.
Okay.
Alright.
Good job, all. Good job.
Yeah, good job.
Yeah, good job, everyone.
Yes.